Overtones are notes of higher frequency than the fundamental frequency, but integral multiples of the fundamental frequency. So that is what overtone is all about. When we talk about overtones, we mean the higher frequency, which are multiple of what the fundamental frequency. And in a closed pipe, we can have something that look like this. That is the other one. You see this one is fundamental frequency. Multiple of it. These are the overtone. The first overtone, second overtone, third overtone, and the fourth overtone, and so on and so forth. In an open pipe, we have also this is the fundamental frequency. We have first overtone, second overtone, third overtone, and fourth overtones. So what we're going to do now is to look at a question that will help us to really understand how to do some work with this. So, in our previous uh, class, we did something on um, resonance. Resonance. In a resonance, you know that it has to do with closed pipe. So, when we talk about closed pipe, actually, um, your mind should be running towards that resonance experiment, which is in which we can see some of these overtones, one, two, three, four, as the case may be. So in this question we have on the board, it says that calculate the frequency of the first overtones of a closed pipe of length 40 cm if the end correction is 5 cm and the velocity of sound is 360 meter per second. 360 meter per second. So if you look at this, you find out that we have something here that should call our attention. It says that end correction. The end correction is what we need. We need to add it up. When we're doing this, remember in the previous video we did something with that. Then let's see how far we can solve this problem. We know that we're looking for what? We're looking for, say, calculate the frequency. We're looking for the frequency. We know that velocity is this, and then the frequency will then be, that is the frequency. In this case now, we have something that is unique. This is the end correction. In this one, we were given the end correction so that we can, if the end correction is this thing, we'll have here 0.5 cm cube, cm, sorry, and then 40 cm as the length. So in that case, where we have end correction, it simply means that for us to calculate that, we should also consider it. In order to consider it, what we mean is that we are going to have our frequency to be where the C stands for the end correction. Now in a closed pipe, or perhaps in resonance tube experiment, you find out that you have, when the tuning fork is up, when you place your tuning fork up here, there's always a gap. This gap is the end connection, which is always use the symbol of C. So from this other end down here is the length. Let's say, okay, we can stop it here. This is the column, the area that contains the water, and we have our wave. This is the notes, and this is the antinode. This is the node and the antinode there. So the end correction is this area, because if you want to get the real length of this, if the end correction is given to you, that means you need to consider this other end of it, the C. the end correction. So that's how we got arrive at this. So now he said we're going to find the words, the first overtone. The first overtone for closed pipe is, the first one is, we have 4. The second one should be, that will give us um, adding up lambda plus 2 lambda will give us 3/4. Yes, that's what we have up over. That means it will be equal to this. That is what we have. So then let's see how we're going to get this thing done. Now we have our, so since we have this thing, we have all the thing information we need. So what we do here is that the length, we have the length, and let's say um, lambda is equal to 4 brackets 40 plus end correction, which is 0.5. 40 plus 0.5 will give us 40.5 all over this, 4 multiplied by 4, and then so the next thing we'll do is that um, 4 multiplying 40.5 will give us 162 cm. 162 cm. So, but we know that we normally use meter, so that means we're going to convert it to meter. If we convert it to meter, lambda will then be meter. So now the first thing we're going to do here is to find the fundamental frequency. The fundamental frequency, which is this 0, f0 there. Then the fundamental frequency will be velocity and speed of sounds over, that will give us 2 2 2 let's say hertz. You can just keep it there, 222.2 hertz. That is what we have. So when we multiply through, then we know that the first overtone is, that's the first overtone. Now it means that the fundamental frequency, which is this one, that will be equal to 3 times, which will give us 3, no, what am I doing? 6, 6, 6, and then finally, this will approximate to this. You can say also 6. That means 6 hertz. So this is the final answer to that, or can you also drop it down to 0.667 hertz as our final answer. All right, thank you so much for being part of the class. And we want to read your comments. Make sure you leave your comment. That's one of the ways we can communicate with our audience. And then if you have not subscribed, make sure you subscribe. Thank you so much.